Hi everyone, lots of things to see today. First of all, I thought I had planned everything well, but I'm disappointed in myself. I realized that there's essentially no time between the moment you finish assignment 2 and the midterm. I thought I had left 1 week between the two, but I think maybe I messed up with the spring break. Anyways, so three options. One, we don't change anything. Two, you only have 1 week to do the assignments. Bear in mind, I still haven't written it. I'm going to post it as soon as I finish. Or three, we postpone by 1 week the midterm. So I'm saying three, but so is there some disagreement in the room? No, I'm going to repeat. So if we don't change anything, you have your midterm right at the same moment you hand in the assignment number 2. Or you just have 1 week less to do the assignment number 2, so I can post the solutions. Or I just postpone the midterm by 1 week. So I'm proposing postponing the midterm by 1 week. So, you know, I don't think since it's in class anyways. Yeah. Yeah, so it's all in your algebra, so it's all in so yeah, that's the thing is I want you to have time to digest everything and okay, so let's do that. So I'll send an email to remind. Yeah, so it means it's a bit late, but yeah, that's the way it is. Can't. The what? Yeah. So it would be so when was it? It was on the 8th. So 1 week, 2 weeks. Yeah, so it was on the. Oh, all right. So yeah. On the 8th, yeah. So let's have it on the. Let's have it on the 15th. Okay, so we're on the 15th. So it's all about yeah, chapter 1 to 5. All right. So that's one thing. Now, I think all of you will have received your assignments. I was told the class average was like 80%. I think it's all right. Some questions were better than others. I think sets caused the problems for some people, I was told. So if we have time at the end of this class, I'm going to say a few things about them. I don't think we're going to have some time, but in case we do. And yeah, so that yeah. Otherwise, I'm going to ask the T to say a few words about it. All right, matrix inversion. So let's start with having some intuition about what we're using. Oh, by the way, matrix inversion is part of this whole these whole ideas of solving system of equations, which we care deeply about. But it's not the most used, but it's something that is makes sense for us to learn. Okay. Using the Gauss-Jordan elimination method. Oh, by the way, Gauss and Gauss-Jordan, if you had doubt, it's the same guy as the Gauss for the rational roots and the Gauss that we're going to see everywhere. So pretty smart, pretty smart. Oops, I'm sorry. Nobody ever calls me, so that's why I don't turn it up. Okay. So let's start with yeah. So what we do, what we want to do, we have ax equals b, and the goal is doing this. So I've written that already. So you pre-multiply by the inverse, and you pre-multiply by the inverse, and then what do we get on the left side? We get identity matrix. So essentially it goes over. So if you have the inverse, then you just have one multiplication to do, and you get the solutions for x. So that this is where we're going. This is why we do it. So let's start with Gauss-Jordan. So this could be not really Gauss-Jordan. This is everything. And now let's start with Gauss-Jordan. So we're not going to do a 4x4. 2x2 is fine because we have other stuff to do. So imagine that the matrix is as follows. So A1, A2, A1, A2. So that's multiplying. Let's just say this is x and y. Could be n equals A3. Okay, so that's my 2x2 system. And note the following. So here I can perfectly well have an identity matrix that's going to pre-multiply this, and it doesn't change anything. So let's just do that. So All right, and now what we're going to do is operations to get rid of this stuff on this side, but it's going to make stuff appear on that side. Every operation that I do on the left side, I have to do the same on the right-hand side. And of course, I'm allowed to do it because all I'm doing is adding or multiplying equations by other equations or other things. And everything is always equal. Yeah, so objective. Let's make that left-hand side. Identity matrix. Using elementary row operation. All right, so let's do this. So step one, what should I do? So I'm going to show you what step one would be, and then you can figure out what step two would be. One, I'm going to say that. So what I want here is an identity matrix. So let's use A1 to get rid of B1. So what I'm going to do here is add to row 2 minus B1 divided by A1 times row 1. And then I'm going to have B1 minus B1. So, becomes plus row 1 multiplied by minus, sorry, multiplied by B1. If I do that, and of course, if I do it on this side, I do the same on the right side. So here I get minus A1. So I get 0 here by design. And here, yeah, I'm going to put everything with the same denominator. That's easier. I'm going to have A2 here, then A1 divided by A1. And then I'm just going to subtract. And yeah, on that side, all I get is this. And here I get 0, so I get the same. Right, so that was step one. Step two, what could I do now? Yeah, the expression is a bit more messy, but we can work with that. Yes. Yes, convert A2 into a, well, yeah, first of all, convert A2 into 0. So what we're going to do is row 1, which will become row 1 minus row 2. And here, what I want is A2 times A2 divided by whatever I had here. So divided by this. So here I'm just going to put the A1 at the numerator there. All right. See where this is going? It's the same thing as before. It's like the Gauss-Jordan elimination. It's any elementary row operations. If I do that, then I'm going to get minus this times And here I get minus this times this. Here I get minus 1 so here, what do we get? Well, A1 cancels with A1. So by design, I should just get A2, but just to be sure. So this cancels with that. And I get A2 here. So A2 minus A2 is 0. And here I get a big, nice mess. So plus, yeah, A1 disappears. B1. Yeah, let's keep the A's in front of the times. So that's here minus. And yeah, I think that's it. Haven't made a mistake. Oh, that's good. So I'll let you copy a bit. So just in case you're, for me, it's easy to do this on my computer, but for you, it might take a few moments. Bear in mind, if you miss details, it's just posted on Moodle every once in a while. Okay. And now what we have to do is, let's do the two together. It's easier. So we are going to have row 1 becomes row 1 multiplied by 1 A1. And then this is going to be a 1. And we're also going to have, at the same moment, because we can do two things at once, row 2 becomes row 2 times 1 over this, so times A divided by A1 minus A2. A1 B2 times minus A2 B1. If I do that, then get. So, oh yeah, this okay, I should have done a bit more work here. And here something should cancel. Minus, yeah, this is the same. All right, this is better. Here I'm just going to multiply everything by this. And here I get 1 by design. Here I still have 0. Here the A1 cancels. Here the A1 cancels. Here this is still 0. A1 B2 minus, yeah, this is 1. And here the A1 cancels. And B1 becomes. And here this stays the same. And I can, you can note already that this A1 B2 minus the A2 B1, that's the same at everywhere. So what I can write is something very easy. So just on minus 1 minus C2 and 4. So how nice is this? Yeah, it's for a 2x2. So it's just things are more complicated when you go to n by n, but the idea is there. So one thing to note, this is, what is this? 1001 is the identity, but is also the reduced row echelon. What's okay? That's that was somebody who was super surprised by, by what I was doing. No kidding, man. Yes. So nice pick, Steve. I'm going to remember that name. No, I'm kidding. I don't remember it. Yeah, that's one thing I wanted to say. So it means, yeah, so it's what we expect. We can invert it. Okay. Yeah, and one thing that we can do too is, so here this is just in matrix form, but if you really would like to know what are x and y, so we can just multiply stuff. And let's do the final multiplication. Some payment there. My pleasure. Okay, let's get rid of this. So here I get for x, so I'm going to this way. So 1 over this. And here for x, I get b2 times a3, or a3 b2 minus a2 b3. And here I get minus d1 a3 plus a1 b3. So, oops. So let's keep the motif the same. So this would be a1 b3. So these are our solutions, which is what we should expect. It's for a 2x2. That's it always looks like this. Yeah, I want to note other things. So does that remind you of something? So yes, what is it? Yeah, it's a determinant. What is this? Here, it looks awfully lot like the denominator, no? It's just that A1 has been changed to A3 and B1 has been changed to B3. But it really looks like a determinant too. It's just a determinant of a different matrix. So no. So we can rewrite this as x equals to ratio of determinants. So this would be the determinant of A1, B2, B1, B2. So you can see this right away. So that's A1, B2 minus B1, A2. And then at the numerator, I have almost the same thing, but instead of A1, I have A3. And instead of B1, I have B3.
No.
Yeah, not yet. But so it's, does that remind somebody of something? So what is this? These two things are, let me put this in A1 and A3 and D3, what are they? If you look at what this was here, they were the constant terms there. So what we did is simply put the constant terms on the first row, and we found x. And we could do the same with y. And with y, what do we get? So the denominator is exactly the same, but here it's B2 has been changed to B3 and A2 has been changed to A3. So the same thing, but I just changed this. And I'm just letting this marinate a bit, and I'm going to discuss more a general way of doing the computing the inverse, but keep this in mind for the end of the class. General case. The general inverse. So now if I ask you a 5 by 5 in the exam, you can do it if I give you enough time. Okay. So, consider a matrix. N by n. Then we have that its inverse is this. 1 over. So this, I guess you can already guess that I should have the determinant on the denominator because that's what I have here. So it's 1 over the determinant of A, which multiplies this matrix there. So minus 1 to the I plus j. So the cofactors are showing up times Eij. So this is the general form for the inverse. So you see it's super simple. So, but obviously it might be a bit more complicated to compute. We're going to do examples, don't worry. Where? A is the determinant of A. And this thing there. Oh yeah, I'm missing a transpose. Transpose, just to add this touch at the end. So transpose. So is the transpose of the cofactor matrix. So now let's just do an example. So it's going to be easier. So let's have a 3x3, shall we? Is okay, so I use 1, 2, 3, and then 1 minus 1, 1, minus. The determinant. Let's compute the determinant. So at the exam, you just look this up. Matrices, determinant. It is 4. So that's how you do it. And now the new stuff. It's the cofactor matrix C. So I'm just calling it C because it has cofactors inside. All right. So I'm going to have a big matrix, but it's going to get some more simple. So for those who are copying everything, I wish you luck. Okay, plus, minus, plus, minus, plus, minus, plus, minus, plus. All right, and now we remove stuff. So each time I'm in one cell, I remove the column and the row corresponding to that cell. Step 1, center, right, bottom left, center, bottom left, and okay. Now let's color this between. So let's just go ahead. So this is let's do it in one go. So 2 minus so yeah, this 5. This is 1 minus 3, so plus, so it becomes plus 2. Minus 1, minus 2, minus 3. So if you're really copying, I can give you some more so you can see the whole thing there. So this is 1, yeah, plus 1, so minus 2, yeah. 0. This is minus 1, minus 2, plus 2. 3 minus 2, so that's minus 1, that's minus 2, so plus 2. No, minus 2, minus 2. And then 2 minus 1, so 1. Let me check. 5, 2. Oh no, I think there's a sign that's wrong. Or maybe it's in my own notes that the sign was wrong. So yeah, this makes sense. No? Yeah, I can check it afterward. Yeah, I think I just made a mistake when I copied it. Okay, because I had a good checker there, so I think it's fine. So now C prime is the transpose of this. So here I get my minus there, becomes plus. Here I get -3. Here I get 1. Here I get 2. -2. And okay. So then that's it. Easy peasy at the exam. There's no way you're going to make a mistake. Yes. So that should be equal to 1/4 times. Okay, now let's see if whether we made a mistake or not. Oh, same. How nice it is. Yeah. So that's how you compute an inverse. So you can pretty much imagine that 4x4 is unmanageable, and I'm not going to give you a 4x4 at the exam. Let me put this even smaller so you can copy if you want a bit. So these are all the operations. Yeah, so just being a student is the art of guessing the exam. So you can guess that I'm not giving you 4x4. 3x3 is, I don't know, maybe. It's doable. I mean, myself, I in my own notes, I made a mistake. Okay, so that was finding the inverse. Yeah, so here I showed you basically how the 2x2 is done, and I show you the general form. I'm not proving you anything about where the general form comes from, but you can more or less see the principle behind it. So that's good enough for me. Now, Kramer's rule. So this is a very neat trick that economists use quite often. So what if I just care about the solution to a single variable? So let me go back to my system there. So this was my system. So we have found that the solution is this. Yeah, so let me just write this more concise. So it's not an accident, and it's something that works in any dimensions. So let me show you a 3x3 example. Um, if I have right, so if I find the solution, with how we just did it, it will be. So this is going to be times this inverse. So, and the inverse is 1 over the determinant. The determinant of this, I'm saying, times, let's have the cofactors here. So really, I'm telling you, if you want to copy, just take a day break today. So it's going to be fine. It's just I like giving you details, but you know, all the details are not necessarily this, this. No, get rid of this and this, this and this, this and this. This and this. I don't forget my minus signs. So let's find x here. X, so this is x, y, z. X is going to be equal to 1 over the determinant. And then I just care about the first row here because I care about x. So I just care about the, oh, and this is, sorry, there's no minus 1. So it's going to be 1 over the determinant that multiplies. Oh, you're right. I think I forgot to transpose it. Oh, yes. Thank you. That would have not worked. Okay, yeah, this works. So I get A4 times this minus B4 times this plus C4 times this. And what did I do here? Well, it's like I computed the determinant of a big matrix using this row, this column A4, B4, and C4. So it's exactly like this. A4, C4, And here I have C3. Here I have so, and here I'm just going to highlight this thing. So maybe you were already believing me with the 2x2, but this is just to make sure that everybody trusts what I'm going to say. So Cramer's rule is a generalization of this idea. So if I have times x b, fine. To find xi, form the matrix I'm going to name it AI by replacing the I column of A with the vector B. And compute psi AI over H. So that's it. That's a neat trick, and it works very, very well. Okay, so I may have lost a few. So I'm just going to step back and see what we have been doing so far. So yeah, so I realized I've written written more than I thought. Okay, so this is what we wanted to do is to find a solution for x all the time. And I've shown you that it's a solution if I just have all I have to do is multiply by the b by the inverse of a, and I get the solution right away. So, and I've showed you that with Gauss-Jordan elimination, this is what the inverse of a 2x2 looks like. So it has this feel to it. But so I don't advise you to use the Gauss-Jordan method every time. Because it takes time and you can mess up. Well, you can mess up in any ways. It's not. I'm being earnest with you. It's never going to get entirely easy. That's just a lot of computation. So it's lots of algebra. Yeah, but the general first formula of the inverse is this. So here I just gave you an example of how you do it. So first you compute the determinant, and then it really looks like the determinant is just the transpose of the cofactor matrix. So the cofactor matrix is the same sort of matrix that you use for the determinant. Here we have to transpose it. I didn't choose that. You have to complain to Gauss, I guess. But he discovered that he didn't. Okay, so then I gave you an example of how you compute an inverse. I'm going to sadly ask you to compute inverses, so you're not going to get away with it. But yeah, if so, my advice, like usual, is it may look like every single operation is trivial in a way, it's just addition, but the way to mess up is to forget a minus sign somewhere. So just be super methodical the way you do it and practice. There's no way around it. And something like forgetting to take the transpose, even I do it many times. And then Kramer's rule is a very neat way to do it quickly. So all you do is say, for instance, I want the solution to this system, and I just want X. So what I do is I replace, so X is the first variable. So I take the constant vector. I put it in the first row, no, in the first column, instead of these coefficients. And I just compute the determinant of this, and I divide by the determinant of the matrix itself, and that gives me the solution for X. Yeah, and that's about it. So lots of things to write down, but essentially this is what you're going to have to do. So do some Kramer, do some inverses, do some determinants, and as they say, do algebra. It keeps you healthy. So now I'm just going to. Oh yeah, so I can give you an example again. Same example as before. So let's do it with just with the with this A matrix. So this. So yeah, so let's have something like times so I always pick my numbers. So give me some numbers there. 1, 7, and then whatever, 0 and 2. Or yeah, let's have a minus. By the way, I just read somewhere that so if you ask people their negative number, they never pick a negative number. It means that people are inherently positive. Okay, so let's find X. So the X should be equal to the determinant of this. But here what I do is I substitute 7, 0, and minus 2. So I'm just going to highlight that this is what I did. Yeah. And I think I'm being nice by making it not too complicated to do it by hand. Oh, no, actually, I did do something complicated. So let's make our lives easier. So imagine this is 0 and 0. Oh, 0 and 0. I hope that I can invert that. All right, 0 and 0. And 0 and 0. So that will be easier. Because then the determinant of this is 1 that multiplies 14 minus 0, so that's 14, that's easy. And here the determinant of this is 1 that multiplies 2 minus 1. So that's equal to divided by 2. 7. So that should be the solution. So well, if I prepare stuff before, I can know that I did have the right solution. Now I'm not sure. So let's check this is just for me. I'm going to check if whether that's the right solution. So so this that multiplies this. Yes. No. 7. Oh yes. This is it's. No, it's okay. We did. Oh yeah, that's not. This is not 2. It's 1. Okay. You see, even I made a mistake. All right. So that was Kramer's rule, and I think, yeah, last example is something from economics at last. So why would you use such a thing? So let's use an example from economics. Let's have the national income model, because we have relied a lot on market equilibrium. So let's use something different. And by the way, in macro, they use this a lot. So we have y equals to consumption plus basic investment level plus basic government expenditure. And we have that consumption is equal to function, positive function, linear function of y. So here, two things are going on. I have two unknowns, y and c, and both are function of the other unknown as well. So how do we do that? Well, we could just solve it like we always do, but let's use Kramer's rule. So first of all, let's express that in matrix form. Let's variable left hand side and constants on the right hand side. So we do this because then it's very easy to express this in matrix form. So I will get y minus c. And here I would get minus dy plus. Now we can express this in matrix form. Well, actually, let me just do it my own way. So my two unknowns are y and c. And my constant terms are whatever is left on that side. So that's y0 plus g0. Oh dear. Yeah, I was almost sure, but I thought there might be a chance. Okay. This is the. And what are my coefficients there? 1 minus 1 minus b and 1. Yes. I think that's it. Yes, it is. Okay, so let's find well, let's find both of them. Oh yeah, did I use a K at some point? Sometimes I forget that. Poor Kramer, I don't write his name properly. Yeah, I think it's C. Yeah. Okay, so Y should be equal to here I get this thing there. So that's so that should be y, and then to make you work a bit. So let's please find C. And I'm going to lock the door. Oh, yes. Yes, sorry. And now please find C. I want at least 2 people to find the right answer before I let you go. So do I have suggestion from that side of the room? Okay. And I'm going to highlight. No idea. Ooh, what's happening? Oh, oh, I didn't know I could do that. From that side of the room, from the backbenchers. Backbenchers have something to share with us. Not really. No, yeah, exactly. You just if I care about C, then I'm going to replace these 2 things and compute the determinants. So did you find it? Did you find it? All right. So is there one person who found it? You did, or oh, you. Okay, somebody. You did? No, you did. Oh, I'm the only one working here. So, or no, we're 2 working, I guess. So what is it? Okay, so let's try that. By the way, I make mistake all the time. You shouldn't trust me. So that's A plus B times I net plus G net divided by the same thing. Yeah. So question about that. Also, it's a procedure, it's a method, it's an algorithm, it's a recipe. So learn it, and you shall be happy for at least for the time of the exam. Then forget about it until you find out that it's useful a year later and learn it again. So that's my message to you. Okay, so if there are no other questions, So I had a small part about, but I think about comparative statics, but I think I want to leave this to second part. So let's just close that. So chapter 5 finished. Yeah. And now I just want to say a few things about sets, because it seems that a few of you had a hard time with them. Okay, so okay, yeah. No, that's not it. Assignment 3. I just want the questions, or maybe if I go to the website. Yeah, this is how organized I am. All right. Okay. So apparently this was not well received by a few people. Yeah. Yeah, proper one. Yeah. Okay, what's going on there? So we define sets, for instance, with a definition of a set. So we say that A equals to A is, here we say what is element R. So we have elements that are formed by a single scalar or a single number, so X. And then we can say that X is included in, oh, is it the same? No, it's a different one. Ah, gee, that's, yeah, exactly. Where is it then? Yes, it should. Oh, Jesus. Ah, why? Okay, no, forget about this. Um, Assignment 1 solution. Maybe I can use the solutions already. Okay, they're the right one. Okay. Yeah, so I'll post these I'll post these on the web, of course, but just maybe I already did. Okay, so bear with me 5 minutes, just to clarify some stuff. So here we're saying X such that X is a part of the natural numbers and X is smaller or equal to 10. So does that ring a bell to some people? Hopefully. Here it's possible to just think of it and understand what I'm defining there. So I'm defining a set with elements that need to fulfill two properties: be in the natural numbers and be smaller or equal to 10. So then what you have to do is you have to ask yourself, so is, say for instance, 1 is part of the natural numbers, is it smaller or equal to 10? Yes, so 1 is part of A. And then you do that for all the possible natural number and you realize that you have 10 of them. So that would be equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that would be your set A. And then your set B would be, here you cannot define it this way because you have an infinite number of elements. So if you do something like this and you say dot dot dot, I'm not happy. So what you would, yeah, what you would, but so the right way to define B is to define B this way. But can, what you can see there is B is made of what? The natural even numbers. How do we know that? Well, because we ask yourself, is one part of the set B? Well, one is a natural number, but one divided by two is 1/2, which is not a natural number. So you know that one is not a natural number. Then is two inside of the set? Yes, two divided by two is natural. And so forth. And then, so this is how you define your sets. So now let's just look at A before I let you go. So here I say there are two possible answers. So you just have to know what you're doing when you're taking the intersection of two sets. You're taking the elements that are part of either one or both one and the other, which means that they have to obey the three conditions. So you could just cheat in some way and say it's part of the natural numbers, smaller or equal to 10, and it's such that x over 2 is part of 10. So you just write it this way. Or you can also remove the odd numbers from the first set, and that gives you the intersection A inter B. I was accepting both set of answers. So if it's still mysterious to you, please come and ask me, because there might be questions about this in the exam. Yeah, so otherwise I'm going to stop here. Unless there are questions, but I feel like you wanna take off. All right. Okay. So thanks everyone.